Hello, my name is Scott Prochaska. I am a field application engineer for Wind River, and I focus on the Simics product. I'm going to spend about 15 minutes demonstrating an integration of MathWorks Simulink, used for system modeling and simulation, and Wind River Simics, which is used for virtual hardware simulation. Now, when using these tools together, a number of workflows are possible. For example, if you're following a model-based design workflow, you'll at some point have a high-fidelity model, some of which you'll want to generate code from. You'll want to compile and execute that code on hardware. This integration handles that code generation, compile and link, and creation of the virtual hardware for the execution of that code, all on your host. In another example workflow, which we refer to as co-simulation, you can have a full software stack, basically your unmodified target binary running on a complex virtualized hardware system in Simics. And you can decide to tie that back to a simulation of an external physical or an environmental system, and Simulink can be perfect for that. In this demonstration, I'm going to focus on model-based design, and more specifically, I'm going to show a workflow around PIL, processor in the loop. PIL provides a way to take a block from a larger system in Simulink, generate code from it, run it on hardware, and tie its inputs and outputs back to the larger model with your plant models. Let's look at some diagrams to help understand the integration. Here's a model in Simulink. It's an aircraft flight control model. You can see that it's made up of a controller, a flight dynamics model, pilot input, and some environmental input, in this case some wind models. Now in a typical workflow, you'll refine this model to a point where it represents a true system. And at that point, you'll want to take the controller block to drive your system requirements and ultimately your software requirements. Or you can generate code directly from that block using embedded coder. Once you have that code, you're going to want to run it on hardware. And you can use PIL to validate the code running on that hardware. In PIL mode, Simulink communicates with the software to pass inputs and outputs back and forth to complete the loop. Now, the first thing that Simics brings to the picture is the ability to virtualize that hardware. The target hardware can include the processor, the peripherals, various buses, all the way up to multiple boards in a complete full hardware system. What this means is that you can have your virtual hardware running generated code from Simulink in PIL mode all on your workstation without the need for physical hardware. This is just the beginning. Many other opportunities open up with hardware virtualization that will affect all phases of your development lifecycle. Let's go through a demonstration of Simulink and Simics working together. I'll start with Simics and MATLAB on the screen here. In Simics, I'll create a new project and then minimize it for now. In MATLAB, I'll bring up Simulink on that model that we just discussed. Now this is a model that ships with Simulink, so you should be able to find more information on it in the help system. At this point, I can click on Run and run this model in normal mode. I can see my pilot input and my system response. What I want to do is configure this system so that it'll generate code and run that code on top of Simics. The first thing I need to do is convert this model from the continuous domain to the discrete domain, at least for the controller, so I can generate code. Then I want to instruct Simulink to use embedded coder and to use the GCC compiler along with Simics for the hardware. And finally, I need to specify the architecture. In this case, it's going to be a Freescale 8641. Now I'm going to click on Run. This time, instead of running in normal mode, Simulink will generate code, invoke the compiler to compile that program, and to run that on top of Simics. And when this code starts to run, Simulink and Simics will work together to facilitate the data between the controller and the plant models inside of Simulink, thus completing the loop. Now notice the pilot input and the system response. And remember, this is generated code running on top of virtualized hardware inside of Simics. Let's take a closer look at Simics. Up until now, we've been using Simics as hardware replacement, and it's been in the background. I'd like to focus now on what we call better than hardware. That is, things that you can do with virtual hardware in Simics that you simply can't do with real hardware. The first better than hardware capability is called a recording checkpoint. Now, when I ran this simulation a moment ago, I was actually recording the execution in Simics, and Simics automatically saved that. And this recording includes all inputs into the hardware system. And given that Simics is precise and deterministic, I can actually reproduce the previous execution exactly. This includes everything like memory, registers, and internal device states. Now at this point, I can double-click on that checkpoint to open it. Alternatively, I could have emailed this to another person or to the team, and they all could have opened it. Let's take a quick look at the hardware first. If I navigate down into my system, I can see that I have one board with a processor and a number of components on that board. Now from this Simics Eclipse perspective, I can create my hardware system and I can interact with that hardware. I can modify it, I can increase the number of processors or devices on my boards and so forth. Let's look at the software now. I'm going to switch from the hardware perspective to the software perspective. And I'm going to set some breakpoints on some interesting lines of code. Now you'll notice at this point I'm on the first line of code at main, and this is the beginning of my recording. And I can now step through my code. I can do all the normal debugging types of things, look at variables and so forth. Now if I run forward, I'm going to run to a breakpoint that I set on the last line of code in the step function for my controller. This is the point at which all of the outputs have been calculated and are about to be sent back to the plant models in Simulink. And those outputs are in some local variables. That means if I run forward from one breakpoint to the next, I can see that the outputs are changing. And remember, we're doing this from a recording, and this involves precise, deterministic execution, which is something that you don't have with real physical hardware. Let's look at another better than hardware capability called reverse execution. Notice up until now I've been running forward through my code, clicking on the step and run forward buttons. Well, notice next to those buttons are step backwards and run backwards buttons. I can actually step backwards through my code, or even run backwards through the code. In this case, if I run back to the previous breakpoint, I can see now that my outputs are changing backwards in time. And as you can well imagine, this is invaluable when debugging. If something happens in your system that propagates and then shows itself later, you can actually step backwards through that propagation to the source of the problem. And since it's captured in a checkpoint, you can email this to a coworker and they can do the same. Now in the first demo, I was working with a bare metal board. In other words, there was no operating system running on it, just our controller code. Simulink and Simics work together directly to facilitate the controller to plant model communications. Here I'm going to run a script to do what we just did, but with the VxWorks operating system. I'm also using a different model. The process is similar. When I click on Run, Simulink will generate code, but then link that, this time, into a VxWorks downloadable module. Simics will then create a virtual board, boot VxWorks from Flash, which will then FTP download our compiled image. When that image containing our controller code starts, Simulink will communicate with it to complete the controller to plant model communications, and thus completing the pill loop. Here you can see the output. In fact, in this example, we're comparing the output of the controller running in Simulink to the output of the controller running on the target hardware. And indeed, they're equal. This is one of the tenets of model-based design. Let's look at one slide to help us understand how Simulink Pill and Simics work under the hood, and see how you might iterate towards a final shipping product. The first diagram shows our first demo today. That is, Simulink connects to Simics to transfer the data back and forth. Simics created the hardware, no operating system was present. And Simics presents the data to the software through a device on the board. The software can use its traditional device drivers to read and write data through that device. And as you can imagine, you can add and extend virtual devices to match your actual hardware. Ultimately, you can run your full software stack unmodified on Simics. The second diagram shows our second demo. In this scenario, Simics provided a virtual board on which VxWorks ran, and data transfer was via TCP/IP. This shows a contrast between data transfer through devices, as in picture 1, and peer data transfer through TCP/IP. And it shows a contrast between a board with and without an operating system. So let's wrap up. Simulink for system design and simulation, and Simics for hardware systems virtualization. The integration supports a number of workflows and a number of possibilities. This includes pill-specific workflows and co-simulation scenarios for larger hardware-software system simulation running full unmodified binaries. That's all for me now. Thank you for your time.